We're looking now at differential equations and trying to understand some of the unexpected behavior we sometimes observe. So even in a simple first order differential equation like this one, even when it's a single equation like this one, sometimes we observe oscillating behavior. So sometimes when we solve the equation and get y as a function of time, we find that the solution is oscillating, and sometimes we'll find that the equation diverges, which means as time goes by, y explodes, right? It may start at some small value, but it raises off to infinity. And then sometimes, on the other hand, we find that as time goes on, the value of y decreases and gets closer and closer to zero. So looking at this equation, we know the solution to this quite easily. So this is nothing but y of t is equal to y naught e to the at. So a is the coefficient of y in this equation, so e to the at. And y naught, of course, is the value of y at t equals 0. So that's the solution, and we can see from this equation that if a is a negative number, then as t goes off to infinity, or as t increases, this is e to the minus increasing number, so this becomes a smaller and smaller number, so that gets closer to 0. So that's why when a is negative and real, then this value of y decreases. And I'm just going to show here a plot that I've done of this. So we'll have a closer look at the code just now, but basically I'm plotting y equals y naught x of at, and I'm setting a equals minus 1 for the real part and the imaginary part to 0. And we are getting an exponential decay here. So that's all expected behavior. Then if a is still real, but if it's more than 0, then y will diverge. And again, we expect that. If a is more than 0, then this is going to be e raised to an increasing power as t increases, and so that's going to increase exponentially. And we can easily see that if we increase the real part. So if we take it away from minus 1 and we keep increasing that, and we can see when the value is 0, then it's a 1 here, so e to the power 0 is a 1. And if we increase it further, you can see it's starting to diverge now. So as this is time being plotted down here, so as t is increasing, the solution is exploding away, and so our function, our value of y is increasing. Right, so that's all expected behavior, and I'm just going to restore that negative value, right? So that's all expected value if a is a real number. Now, if a is a complex number, then we can rewrite this factor as e to the, we can expand a, if it's a complex number, into a real part and a complex part. So sigma is the real part of a, and omega is the imaginary part there. And we know from our complex number, the basics of complex numbers, so the Euler expansion of this is going to be e to the sigma multiplied with cos of omega t plus I sine of omega t. So that's shown here. Right, so that's how we expand an exponentiation of a complex number. We get the exponential of the real part plus these trigonometric features from the imaginary part. And so let's have a look at what that gives us when we have an imaginary part for a. So omega is the imaginary part, the coefficient for the imaginary part. As we increase that, we can start to see that the curve becomes slightly more complex, and we increase that further, and as we increase that, you can see the oscillation increasing there. And in fact, I'm going to increase that further. I'm a little bit limited by what I can do here. So I'm going to change this initial value. Let's just give it a value of 10 here. So you can see now a very strong oscillation, and it does die out, and that's because we still have a negative real part here. Right, so here we have out as a multiplying factor a value which is e to the negative some value times t. So as t increases, this number is going to decrease and get closer and closer to 0. So even though there are oscillations, this is going to tend to kill off those oscillations. And we can consider how that changes if we reduce that that exponential die-off. So let's say this number was becoming more positive, right? So we are increasing our value of the real part. It's getting closer and closer to 0. Now you can see the oscillation is persisting for a greater period of time. And now when we go to 0, there's the real part no longer exists. So the real part is a 0. And if we look back here, when the real part is 0, this is e to the 0, which is a 1, leaving us just with trigonometric functions here. So we are going to get a cos function for the real part of the solution and a sine wave on the imaginary part. And you can see that here we have plotted the real and imaginary parts of our solution. And in fact, I'm going to reduce this omega. Okay, so as we reduce the imaginary part, then we can see the frequency of the solution decreases as well. Right, so this real part, if we reduce the real part, again, that's going to cause our oscillation to damp out. If we increase it past 0, then you can see our solution is starting to diverge away. So in this case, our function is blowing up. The values are oscillating between increasingly large values. So this is how in a single simple first order equation we can achieve all this sort of complexity. So there are these 4 features to concern ourselves with, right? Is the function blowing up? Is it diverging? Is it converging? Is it oscillating? And to start understanding whether or not those features exist, it is useful for us to plot, instead of plotting the real part and imaginary parts as functions of time, we instead can plot the phase plane, where we take the imaginary part and plot that against the real part. And to construct such a figure, you can imagine taking time slices here. So looking back in this time domain figure, if we take slices here in time, if we pick any time, let's say we consider time 0. At time 0, we have the real part being a 1 and the imaginary part being a 0. And you can see that here. So the real part is a 1 and the imaginary part is a 0. And we can see here as time increases, our real part decreases and our imaginary part decreases. So both decrease like this. And then we get to a stage where the imaginary part starts to increase while the real part is still decreasing. So the imaginary part starts increasing while the real part is still decreasing. And then we see the oscillations, and we are basically spiraling into this point, which is at 0, 0. And you can see here in our solution, this is reaching 0 and 0 for both the imaginary and the real parts. So what we are plotting here is the so-called phase plane. We are just viewing the 2 components of our solution, the real part and the imaginary part. And so these are the interesting features that arise in this equation. And of course, you might say, well, you've found all these features that you call interesting just because you've gone and forced imaginary numbers into your solution. And it is true you will not see oscillations without applying imaginary parts into your equation. But the fact is, imaginary parts occur far more commonly than we might anticipate. So in the simple equation, the only way to cause imaginary parts to arise is to apply them in our coefficient. But if we consider other associated systems, if we consider second-order systems, it's very easy for imaginary parts to sneak into our equations. And we'll be looking in some detail at some examples where that happens. So anyway, let's look at a second-order system. So in the first-order case, we had a times y. Here we are representing a linear second-order equation like this. So it's d2y dt squared plus b dy dt plus cy equals 0. That's our differential equation. And we would like to get rid of the second order term. We would like to represent our system with first order equations rather than second order. And it's very easy to drop the order of an equation by introducing variables in this way. So we introduce a variable y1 that's directly equal to our solution y. That's kind of a trivial assignment. The more interesting one here is defining y2, which is the first derivative of y. And the reason we do that is because we can then read the first term here as dy2 dt instead of d2y dt squared. So we've dropped the order. So we now have this in apparently first order form. And then for the second term, we can replace this dy dt by y2 just by definition. So this becomes by2. And then cy, we should write this as cy1 because we are now translating our equation into these new definitions. Right now, we can't solve this equation by itself because there are two time functions here. There's y2 and y1. So we have to retain this, this equation. So while it's true this arose just from a definition, it is still a relationship between y1 and y2 that we need to maintain. So we say that the complete set of equations required to solve this system is dy1 dt equals y2, and then dy2 dt plus by2 plus cy equals 0. So that's the set of equations which is equivalent to the single second order set of equations. So we can convert a second order equation into two first order equations. Going on, we describe this case for a linear system, but it doesn't have to be linear. We can still apply this method even if it's nonlinear. So if we consider this general form, if we have some function of the second derivative of y plus some other function of the first derivative of y plus yet some other function of y itself plus some other constant in time, then again we can apply the same transformation, and we would then rewrite this equation as dy2 dt plus f1 y2 plus f0 y1 plus c of t equals 0. And the closed system of equations then is the definition equation plus that equation. And now, yes, it's true that it might not be trivial to solve this equation. It might mean that we have to actually perform some algebraic manipulation, or we might even have to numerically solve this equation to extract dy2 dt. But we can still do it. In some hypothetical integration algorithm, we can certainly look for a solution for this equation. And so there exists some number dy2 dt, right? If we view that as a number, and these also as numbers at some current state, then there exists some solution to this equation, dy2 dt, which we can find. And then that with dy1 dt means we have the gradient at some local point, and we can span out some solution. So even in the case of nonlinear equations, it is still true that we can drop the order of the equation and get for ourselves two first order equations, and those may be nonlinear, but they will be first order. So yes, we can get first order equations. We can get a system of first order equations. And we still haven't yet described how the imaginary part can sneak in there. We'll get to that just now. Now we want to look at solving systems of linear first order equations. So let's say, generally speaking, we had an nth order equation, and we dropped the order until we arrived at a first order equation. And even if it was nonlinear, we could still linearize that equation by taking a Taylor series expansion close to some steady state value. So we could linearize a nonlinear equation, and so generally speaking, we have systems of first order equations. So it doesn't matter if the equation was high order to begin with. We could always drop that order and get to a system, to an increased number of first order equations. It doesn't matter if we had nonlinearity in the equation. We could still linearize close to steady states, and we could find the equivalent set of equations. And let's just try and understand what we have here. So on the left-hand side, you can see first order terms in the derivative. So in our system of equations, we have some vector y, which has elements y1, y2 up to yn. So there are yn equations. So it's a system of equations in yn. And in a general linear equation, you may have some interaction among all those derivatives. So if it's a linear system of equations, there may be some constants, and so all those derivatives may be involved simultaneously in one equation. And that can be arranged on the left-hand side. So this is the part where the derivative sits. And then on the right-hand side, we have also linear in y. We have some coefficient times y. And we have then each y element in the y vector multiplied by some constant. So of course, this would be an extreme case where all the terms are active. But of course, quite often some of those terms will be switched off simply by setting the coefficients to 0. But anyway, that is a general first order equation where all the y elements are interacting. And we may have n such equations. So if we have n differential equations in n variables, then we can represent them with these different equations like this. And you can see here the coefficients are changing in their subscripts. So all the coefficients for the first equation, for the coefficients associated with y1, the first argument of that coefficient is telling us which equation number we are looking at, and the second one is telling us which element of y is being multiplied in that first equation as that contribution. So that's for this first equation. Then you can see for the second equation, the first argument of the coefficient is a 2, and we can repeat that until we reach the nth equation, and so on. So that is, generally speaking, our system of first order linear equations in y. Now, if we look at this, we can think about creating, we've already said we can create the vector y. We can create y as a column vector. So down the column we have y1, y2, yn, and of course I'm using a transpose here to make this a column vector. So that's y. And then we could also write dy dt is ddt of y1, ddt of y2, and up to ddt of yn. So we could say that this this kind of verbose left-hand side, we can instead represent that by the matrix M multiplied by the derivative dy dt, where y is a vector. So that is a much more compact representation of our left-hand side here. And similarly, on the right-hand side, we can see our vector y, and that's the same as this vector. And if we create the matrix A primed, where A primed is simply these coefficients A11, A12, A1n, A21, A22, and so on up to ANN. If we create the square matrix of all those coefficients as A primed, then the right-hand side can also be more compactly represented as A primed dot multiplied by y. So that's the vector matrix version of the same set of equations. And clearly these are square matrices, and if M is invertible, then we multiply left and right hand side by the inverse of M to give us the identity here, and then M inverted times A primed. And so M inverted times A primed, if we define that to be A, then this whole thing can be written more simply like so. And so you can see that's why I used the prime there. I knew I wanted to use an A in here. Right, so we accept then that our system of equations can be represented quite compactly like that. And please note that we have not gone and separated, we haven't achieved any separation of our variables. When we multiply this out here, we are still going to get this big slurry of stuff here, right? So this is by no means any attempt to simplify this equation. We haven't simplified it. Behind this this expression right here, we still have all these terms when we multiply the whole thing out, right? So that's just representing this again. This is now a vector matrix form, which is hiding all this complexity, even though it appears to be very, very similar to our single equation form that we had originally here. So let's keep going. We've just represented it more compactly so far. And now we want to think about an eigen-style approach to make progress to find a solution here. So, of course, in an eigen approach, we start out by proposing that associated with this matrix A, there exists some set of vectors, and if we arrange those vectors in the column space of a new matrix V, then associated with those vectors will be some set of values lambda. And V and lambda will be such that if you multiply the vector Vi, so if you take the ith vector, the ith column of V, and if you take A times that ith column, then we know that's going to be a matrix times a vector. That's going to give us back a vector. And we are saying that this vector V is such that when you multiply and you get that new vector, then you will get the same result if you multiply the associated lambda by that same vector. So we aren't multiplying lambda by A, we are multiplying lambda by V. Right, so yeah, instead of pointing all over the place, this is what I just said there. So if we take the ith vector of V, if we take A times that ith vector, then we'll get out a vector which will be the same result that we get if we take the ith value of lambda, and that's a scalar, right? Lambda is a set of values, it's a vector of values, and if we take out just one of those values and we multiply it with the associated vector, which is the same as this vector, if we multiply this is a scalar times a vector, so that gives us a vector. This is a matrix times a vector, also gives us a vector. Then those two will be equal. And we haven't proved anything, we haven't said anything about how we find lambda and V. We are just saying, in a way, this is kind of our wishful thinking. We are saying, I would really like it if there was this nice vector v that had this property that it also had a value lambda. So if I multiplied a by that v, then I'll get a vector which, if I have this other magic number lambda, that if I multiplied by v, I would get the same result. So this is very much something that we are supposing exists and that we are proposing to happen. And in fact, yes, we know that this does happen, and we can find such numbers. We can find a vector and a number that has this property. And the reason this this supposition or this proposal or this hope is useful, we'll see in terms of solving this equation. So we have this relationship, which is largely a result of our own definition. And we will now say, let capital lambda be the matrix of lambda arranged on the diagonal. So we know lambda is some vector of values, but instead of arranging it as a vector, if we say, let's make a matrix, and I think it looks like this, right? Let's make a matrix, and then just ignore the exponential here. If we, in the diagonal, if we write here lambda 1, if we write lambda 2, lambda n, right, then that will be our capital lambda that's proposed here. So capital lambda is the matrix that we get by taking a zero matrix and just writing lambda on the diagonal of that matrix. Then we have a form like this, all right? So instead of now choosing a particular value, a particular vector out of V, we can take the entire matrix of all the vectors written in the column space. And so it's A times V, AV is capital lambda times V. So now we have a nice matrix equals matrix, and we can think about doing operations on both sides. So we can first of all multiply this equation by V inverse. And I see here that I should write it this way. Right, and in fact, in the case of these two matrices, it doesn't matter which way around you multiply them, because you've got a diagonalized matrix, so you can write V out here instead. And now if we multiply both sides of this equation by V inverse, then the left-hand side is simply V inverse AV, and on the right-hand side it's going to be V inverse times V, which is the identity matrix. So you could write this as I capital lambda, but of course we can also just write that as lambda. So now we have this form of the equation, right? Again, it started out from our wishful thinking that there existed this kind of arrangement, but a consequence of this hope of ours is that we can then create a matrix which is fully diagonalized, which only has non-zero entries on its diagonal, and those entries will be lambda. And we can relate that to these associated so-called eigenvectors in this way. We take the inverse of that column space multiplied with our original matrix A, and then multiplied by that vector V. So this is how we diagonalize our form. This is how we can find the lambda values. If we can, so it becomes, if we can find V, we can find lambda. So that's all well and good, right? That's 3 lines of wishful thinking. But let's see how that applies now. So we know this equation is a complex system of equations, which is all this stuff. And what makes it difficult to solve this equation is that we've got all these y's here, right? So even if this was quite simple, even if we didn't have all these terms on the left-hand side, let's say it was just that, still we don't know how to integrate this equation, because we have all these unspecified time functions here, right? Fine, we are fine with if we have y1 here, then it's an equation in one variable. But unfortunately, this equation is not in one variable. It's got every possible variable stuffed in there. So, however, we now have this diagonalizing property. And so we can say, well, we've got this complicated equation here, and we're going to say, well, let's imagine that we didn't have all this complication, and instead we had this nice other vector z, which had this property that dz dt is equal to lambda z. Now, in this case, it's totally different from this case, right? In this case, when we have a lambda instead of an a, this is diagonalized. That means we only have a value in the position that multiplies for that specific value of the vector. And in fact, let's try and draw that out a bit. So we have a lambda 1 here, let's say. Lambda 1, and then we'll have 0, 0, and 0. Let's say it was 4. Let's say there were 4 like that. And then let's say we had, let's say that was the second line of the matrix and the third and the fourth line. And so we would have here a 0, and we would knock off one of these zeros, and this would be a 2, and so on. So let's just do it with 3. So this is our matrix capital lambda, and we are multiplying that now by our z vector. So we would have out here z1 like that, z2, z3. And so you see, when you multiply this vector by this vector, you will only have z1 up here. So it's going to be dz1 dt equals lambda 1 z1. Then if you multiply this vector by this vector, you'll only get lambda 2 z2. So your second equation will be dz2 dt lambda 2 z2. And then similarly, if you multiply out here, multiply that vector by that vector, you'll only have left lambda 3 z3. So you'll have dz3 dt equals lambda 3 z3. So that's a fully separated system of equations, which is very easy to solve. And so we can solve that system of equations just using the simple scalar equation that we saw before. So that's what we can get for z. But z was completely wishful thinking again. As yet, we have no connection with our system. So the system of, the problem we have to solve is this one. This is a very desirable system. This is a very easy system to solve. But we notice here that if we multiply or if we substitute for this capital lambda, right? Remember up here, we found that according to our definition, capital lambda was V inverted A times V. So V inverted A times V can be substituted for this lambda. And then if we multiply both sides of this equation by V, right? So it's going to be V dz dt. And then if we multiply V on this side, then this becomes the identity matrix, leaving us with AVZ. AVZ. So this is the new equation, and now we notice here that V is nothing but a matrix of constants. If that's the case, we could say that if we were differentiating V times Z, then because v is a constant, this would emerge as a constant of differentiation. And so we will have v dz dt. So in other words, we could take this part of the equation and say, well, this thing is nothing but d dt of vz. So we write that here. That's simply equal to d dt of vz. And then on this side of the equation, we can also group the v and z together like so. And now if you look at this equation, you see it is identical to our original equation, right? We have d dt of some vector equals a times that vector. So here we've got d dt of a vector, right? V is a matrix and z is a vector, so that's a vector. So we've got d dt of some vector being equal to the matrix A times that vector. In other words, this product v times z is nothing but y. So that's the same as our original equation. In other words, y equals v times z. And so that's revealed to us this exciting transformation we can do. We've got y, which is a complicated function of itself. There are many interrelationships among all these y's. And now it turns out that we can very easily unravel all that, and we can translate it into another vector z, which is fully separable. It's separated. There's no interaction in terms of the in terms of the equation, in terms of the differential equations. This is a fully separated set of differential equations. And that's how we solve these equations. We translate from y to z. We solve the system in the z domain, and we translate that solution back into the y domain. So this is a very easy problem to solve then if we can find this matrix V. And of course, V being the column vector space of the eigenvalues of A, we can find V for A. So for any matrix A, we can find the eigenvectors and eigenvalues lambda. So here it's explained in a bit more detail. In fact, some of the separation of Z that I explained earlier is shown better here, and so we can see more clearly here that we can solve in the Z domain. We can solve Z1 as a function of t, as Z1 the initial value of Z1 multiplied with e to the lambda t, right? Remember, it's lambda 1 Z1. So this is e to the lambda 1 t. And so for each of our equations in Z, we can write e to the associated lambda value t. And so that's our solution in the Z domain. And of course, these initial conditions, the initial values of Z, we can get by using our transformation. So we have the transformation from y to z and z to y. So instead of using y, we can use the initial condition for y, and we can get the initial condition for z. Right? And so we can say, now that we can solve for z of t, we can translate that into y of t, and that's basically our solution. And in fact, we also have this nice definition of the matrix exponential. So in the case of the exponential of a matrix, right here, it's t is a scalar, so there's some current real-time t, and then A is a matrix of constants. So a matrix times a scalar is a matrix. So it's the exponential of a matrix here. This exponential is defined like this. So the matrix exponential is the column vector matrix of the eigenvectors multiplied with the diagonalized exponential of the eigenvalues, and then multiplied by the inverse of the column space eigenvectors. Right? So with this simple definition, we can then write y of t is e to the at y naught. And in fact, this then gives us the exact same form as we had earlier for the simple scalar first order system. Right, so that's our solution to the very general first order case. And please note, it's not just a notation shift here. There is a lot going on behind this exponentiation. So please follow this line of logic carefully and be sure you agree that this is now our solution. And importantly here, we can see that our time constants are these lambda values. And those lambdas can be, those lambdas are generally speaking complex numbers. So in a kind of complicated way, we've shown that you can get complex numbers in your solution, right? Because if you review the calculation of eigenvalues and eigenvectors, which involves matrix inversion and evaluation of the determinant, you can easily wind up with complex numbers for your eigenvalues. So that's one kind of roundabout motivation for the fact that you can end up with imaginary numbers in your exponentiation, even though your original problem didn't have them. So our original A matrix might not have shown any imaginary numbers, but even so, we can still observe them. And in fact, let's look at a simple example where that's the case. So here, I'm going to choose the linear equation. We'll look at the other equations just now. Let's take the simple linear case, right? This is A times y1 plus B times y2. Remember, in computer language, 0 is a 1, and the first position is indexed with a 0, and the second position is indexed by a 1. So let's write the system of equations out so that we can follow that more clearly. So we are writing for ourselves the system of equations dy1 dt equals, and it's going to be minus y2, and dy2 dt equals minus y1. Right, let's just check that's what we have. So yeah, so this is the first, so this is dy1 dt. So a is 0, so this term doesn't exist. B is a 1, so this we read as y2. So this is dy1 dt equals y2, which we can see here. And yeah, that B is a 1, so let's leave that on a 1. And then here we have for C, we have dy2 dt equals minus dy1 dt. So dy2 dt is minus y1. And then the d we set as a 0 here. So let's graph that, and we can have a look later at what all that code is doing. And I'm going, okay, it's fine like this. So let's run this. And look at that, oscillations. So we have oscillations in y1 and y2. So clearly there's an imaginary part behind our system of equations. And if we look at our equations, right, we've done nothing but graph these two equations. There's no imaginary number in sight here, right? This is as simple a system of first order equations as we can get. And we haven't included complex numbers anywhere. There's only a 1 and a minus 1 as coefficients in the system of equations. And yet we are seeing these oscillations in our process. So clearly there is an imaginary number at work. Somehow behind the system of equations there is this imaginary number. And in fact, let's see if we can work out where that comes from. So the eigenvalues that are associated with the system of equations, there is clearly an imaginary number there, and in fact we are going to do that in detail just now. So let's move on from there. So that is what we get in this case, and you can see here the phase plane for that. So y1 and y2 are related in that way. If we change the initial conditions, we are just shifting where we'll start out. So if we shift that, you can see the solution shifts out. It gets bigger as we increase the starting value there. Let's bring that back down. And let's play around with these constants. Let's imagine that instead of a 0 here, let's say we had a minus 0.5. So looking here, if we use a minus 0.5, then that means we have minus 0.5 times y1. And if we think about this, this means that we are going to be damping out our oscillation, right? We are going to reduce the value in y1 due to the presence of this term. So we expect that it's going to oscillate, but that oscillation will die down after some time. So let's apply that here. So instead of 0, it's a minus 0.5. If we run that, you can see, yes, we've got the oscillation, but it's damping out. And you can also see that in the phase plane, our arrows are showing us that the solution spirals in towards the 0 now. It doesn't just keep circling around. What happens if we reverse that? If instead of minus 0.5, it's a plus 0.5. So here in our equation, if it's a plus 0.5, then you can see there's a growing exponential that's behind that relationship. So if we run that, we can see here now the solution is diverging and it's growing outwards. And here we started in at, I think it was 1 and 0, or 1 and 1. So now the solution is diverging out from there. And it's gone past the boundaries I set here, where I drew the phase plane with the little arrows and so on. I drew that only between 2 and minus 2, I think it was. So behind this apparently well-behaved first-order system, there's hidden an imaginary number which is causing the appearance of our oscillations. Okay, and we can look at this gallery of equations. So there are a couple more equations that are interesting to look at. So let's change the type here. And you can see in this case, okay, let's try and shift the initial condition in a bit. Up. Well, anyway, you can see here, okay, let's change this. So by tweaking these parameters, we can view different parts of the phase plane. So you can see here, this system of equations looks fairly innocent again. So this is a square limit set, and the dy dt, dy1 dt is equal to y2 minus a half y1, and then dy2 dt is equal to sine of y1. So that's the system of equations, and we can see here two attractors. So if we start out here, the system spirals into that steady state, whereas if we start a little closer down here, it spirals into this other steady state. So here we've started at 1, 1, so at 1, 1 we spiral in here. Let's instead try and start somewhere down here. So let's look at 2 and minus 4. So initial condition is 2 and minus 4. and you can see if you start there, it's going to fall into that other steady state instead of falling into that one. So all this complex behavior we find behind this apparently very simple system of equations. Let's look at another one, the Duffing equation, or Duffing's equation. And here we have this interesting feature. I'm just going to tighten up our range a bit. So here we've started out at this 2 minus 4 value, and it's danced around a little bit, but it eventually settles down on this stable orbit, and the system just keeps oscillating around here. So you can see here initially dances around a bit, but then it settles down into this oscillating pattern. And that's when we start outside here. So if we start anywhere outside, and we can see that, let's say we drag this to lower numbers. So we've shifted the initial condition here, so it's settled in there. Now let's try and pull that in here. Let's say if we start at 0, 0, what happens? So if we start at 0, 0, 0 is actually a repulsor, right? We've started at 0, 0. The 0 is a repulsor, so it pushes us away from the 0, and we get pushed out onto this, onto the same stable orbit. So we do keep cycling in the same way out here. So in this equation, and again, a very innocent looking equation, but for this equation, we have this one stable orbit. We have no steady states, or no stable steady states. So we never settle into a fixed number. We will always end up on this stable orbit. So this system doesn't have a stable steady state. It has a stable orbit only. And that's, again, complexity that was hidden behind apparently simple equations. So again, the last two examples were not first-order equations, but always we could linearize our first-order equations near a stable point, or near a steady state. And so we can get the linearized set of equations, and we can see then that in our linearized set of equations, we are going to get in the solution the sum of exponentials raised to the power eigenvalue multiplied with time. And that eigenvalue is generally a complex number, and that's going to give us oscillations if the imaginary part is not 0. And then the real part, if it's positive, is going to give us a diverging solution. If the real part is negative, it's going to converge instead. And so, generally speaking, we are getting solutions that that are linear combinations of these types of terms. And we promised all along to show how imaginary numbers could easily arise. And let's look at a simple linear second-order equation like this one. We know that it has this solution. So this equation has this solution. And you can get that either by the classical integration by parts, or by doing Laplace transformations. So there are two well-known ways of showing that this equation has this solution. And as part of that derivation, you show that the time constants tau1 and tau2 are the negative inverse roots of the associated characteristic equation. So if you look at this equation here, the coefficients are A, B, C, and you can see it's second order, first order, 0 order. So the associated characteristic equation is ax squared plus bx plus c. So the roots of this equation are the inverse negative time constants tau1 and tau2. And so if we have any imaginary parts, if we have any complex numbers as our roots, then our time constants are going to be imaginary, and then we will get these oscillating components. And clearly, we can get imaginary solutions here. So if b squared minus 4ac is less than 0, then obviously we are getting imaginary parts. Imaginary parts, we are getting complex numbers for the roots of our equation, and so we'll get oscillations. Right? And furthermore, we can also say if those roots, if the real parts of those roots are positive, then it's diverging, it's a repulsor. If on the other hand, the roots have real parts which are all negative, then it's an attractor. And those are all the features that we need to look for to fully describe our system of equations. So in summary, whatever our system is, we can translate it into a system of first order differential equations. We can then evaluate, we can find a matrix or matrices of constants that summarize that description, and then we can find the eigenvalues for that matrix. And we can then examine those eigenvalues. If those eigenvalues contain imaginary parts, we are going to see oscillations. If there are any real parts with the positive numbers, it's going to be a repulsor. If all the parts are negative, then it's going to be an attractor. So that gives us a tremendously powerful way of being able to predict what's going to happen with our equation. So whatever equation we have, we can look at that equation, translate it into systems of first order equations, and then comment directly on how that equation is going to behave itself. And so this is, of course, a critical thing for us to know about our process if we ever hope to design controllers